Alright, grade 12 chemistry. We're into a new unit. It's called equilibrium, chemical equilibrium. The main point of this unit is really to explore systems of chemical reactions. So, multiple reactions happening at the same time, and then messing with that system, changing the temperature, changing the concentrations, and things like that. We're also going to talk about acids and bases and do some other stuff like that in this unit. But first we're going to do an introduction. So this is the introduction to equilibrium, and here's what we're going to do. We're going to start with just a basic intro to what it is, then some examples of dynamic equilibriums in everyday life. Then we'll talk about something called LeChatelier's principle. We're going to link that to the previous unit, the thermochemistry unit. So without further ado, let's get into it. All reactions are reversible. We've just learned that. Right? You can reverse any reaction as long as you put in energy instead of taking it out, or whatever. You have to reverse the energy. So for example, if you're combusting methanol, you release energy. You could theoretically take CO2 and H2O and add in energy and make methanol. And people have done this. They've made reactors that will make methanol using, solar power or something like that. And then you can burn the same methanol. It's kind of like closing the loop on CO2. It's kind of cool. They're all reversible. And if they're all reversible, then there's a forward reaction and then there's a reverse reaction. And this depends on how it's written. There's no official way to write a reaction. So here, for example, is HCl together versus H and Cl apart, right? That's a reaction. The reality here is that both reactions actually happen at once. And so we need a way to write the reaction as a forward and reverse process. This is what we call an equilibrium process. And so we have this symbol. This is what's called the equilibrium symbol, the equilibrium arrows. And it shows it's a half arrow one way and a half arrow the other way. It's showing that the process can go both ways. And the reason for that is surprisingly simple. Now that we've done the thermochem, right? Here's a reaction diagram, right? A potential energy diagram. This one's exothermic, so you release energy going this way. So there's a small activation energy this way, but a big one going the other way. But, all it takes is the collision. So if you have enough energy to go the other way, it's going to go. If you have the collision at the right energy and the right orientation, your products can become reactants, right? So it's, really both can happen at the same time because you've got all the ingredients there as long as you've got enough energy. So that's why it says up here, right? All reactions are reversible, but some are very hard to reverse. So there are, it's very unlikely that, for example, CO2 and H2O are just going to bump into each other and make methane. That would be a very, very difficult reaction to do. Meanwhile, the forward reaction is very easy, but theoretically you could set it up where you have a reversed reaction of that. Yeah, so that's something to understand, is this symbol, this equilibrium symbol means that there is a forward process and a reverse process. So you've got HCl falling apart, and then H and Cl getting together to make HCl, and then, there's a process. This happens to be very exothermic, so it's very heavily favored on this side, but it is possible to go the other way, theoretically. All right, so that's forward and reverse reactions. That's an intro to equilibrium. Now we're going to get into some examples of dynamic equilibrium. So I'm going to pause for a sec. So these are not actually perfect examples of dynamic equilibrium because we need that equilibrium piece. But there's going to be an example of a dynamic equilibrium that I'll show you as a YouTube video after. The concept is that there needs to be a forward and reverse process. But the equilibrium is a steady state where the forward process and the reverse process have the same rate. So the net amount of material doesn't change. So here's some examples of things that have the same forward and reverse rate and where the total amount of material doesn't change. The first example is cars on a highway. Imagine you live near a highway and you take a picture of the highway and there's, 25 cars on the highway, right? And you wait like 5 minutes and you take a picture again and there's 25 cars again. But they're all different cars. What happened? Right? Well, you have a forward rate and a reverse rate. There's cars leaving the highway because they're moving down the highway, and there's new cars coming into the highway. So you've got a steady number of cars on the highway, but some of them are leaving and some of them are coming in. So that's an example of a dynamic equilibrium. As long as the number of cars leaving is equal to the number of cars coming in, you've got the same number of cars. They're different cars each time. Another example is how much cash you have, assuming that you spend exactly as much as you earn, which you shouldn't. You should be saving something, but just think about it. If you make, I don't know, $500 a week and you spend $500 a week, you're going to have the same amount of money in your pockets. That one's, most people, that's not a dynamic equilibrium. Most people are either gaining money or losing money slowly, but it's an idea. And then the shower is another really good example of a dynamic equilibrium. You've got a forward process, which is the water coming out of the shower head. You got a reverse process, which is it going down the drain, and you've got an equilibrium there. In fact, that's probably the best example of an equilibrium out of these three, because if you increase the amount of water coming out of the shower, the water will come up a little bit higher, but then it'll go down the drain faster, and so it'll actually keep itself pretty stable, which is pretty nice. Yeah. But the important point here about dynamic equilibrium is that when the equilibrium reaction is complete, quote unquote complete, when we've reached a stable equilibrium state, the reactions are still going. It's just that the forward and reverse reactions now have the same rate. So imagine like the highway was closed for road work, and then suddenly they opened the highway. Well, now suddenly cars are gonna, there were no cars, now there's a bunch of cars, but then it'll stabilize to a certain amount of cars. So that's what we're seeing here. Right? We start with, for example, this equilibrium, water and carbon monoxide to hydrogen gas and carbon dioxide. We use the equilibrium symbol. Let's put that over here, the equilibrium symbol. Or some people use the double-headed arrow, but most people use this. If we start with only carbon monoxide and water, only the products, right? The concentration is quite high at the start, and then it drops. And the concentration of CO2 and H2 go up. And then the concentrations become equal. And that, by analogy, is like when the amount of cars on the highway become equal. Right? So this might be the cars entering the highway. This might be the cars leaving the highway. At the start, they're all entering, and none of them are leaving. Then more and more of them start leaving the highway, and then you get this balance. But that doesn't mean that the rate has stopped. It doesn't mean that the reaction has stopped. We've just reached equilibrium. There's still water and CO2 becoming H2 and CO, but there's the same amount of H2 and CO2 becoming water and carbon monoxide at the same time. You'll see a lot of equilibriums in gas phase reactants. Next is I'll show you a YouTube video of probably the greatest demo of equilibrium, and sadly I can't do this in class. Usually I do this one in class. So let's go over to YouTube here. So this is a very simple demo. You've got two big beakers, and these guys have cups, and they're going to just put the cups in. Well, you'll see. Right. So you notice that there's a forward and a reverse reaction happening. Right, there's a forward and a reverse reaction happening, but the amount of water in the beakers stays the same because the forward and reverse is at the same rate. But then you can kind of mess with this, right? They're going to set up right like this. Right, now there's not a lot of water here and a lot of water here. What do you think is going to happen? Well, actually, sorry. Well, it's not a lot of water here and a lot of. Sorry, other way around. Now she's going to get a big cup, and he's going to have a little cup. That's what's going to happen. The big cup and the little cup. There's the big cup, right? She gets a big cup. He gets a little cup. So what's going to happen? We can predict. She has a big cup. It'll be easier for her to scoop water from her side to his side. And so this demonstrates if the forward rate was, easier to accomplish than the backward rate, than the reverse rate. So maybe the forward rate is exothermic and releases energy, and the backwards rate isn't. Maybe the forward rate has a higher activation energy and the backward rate doesn't. So you see here that she can get a lot more water in one shot. But then something interesting is going to happen as this occurs. Right? Notice that now she's having more trouble picking up water. Right? She's having more trouble picking up water, but he can still get a full cup every time. So this shows you that no matter what, she can't get rid of all of her water, basically. Right? So the bigger cup makes the fact that it's easier to go one way and harder to go the other way doesn't mean that she's going to completely empty this beaker. It's going to be lower, but there's more on that side, which is quite cool. Right? You see how that's working. Right? So she's gonna have a hard time getting that amount. And then you can imagine that it doesn't matter where we start. You're always going to end up with the same equilibrium, because if they were back to equal, it'll end up back here. If we had more of it here and less of it here, she'd have a big cup and it'd be easier for her to push water over to his side. That's probably the best demo for equilibrium that you can possibly do. I'll have a link to this video down below so you can see it with sound and everything. Yeah. All right, so yeah, back to this. That's equilibrium. Here's a few different examples of real chemical equilibria. So here's the Haber-Bosch process. It's nitrogen and hydrogen gases making ammonia gas. This is what makes a lot of our fertilizer. And it's going back and forth, back and forth, back and forth, back and forth. So these two, nitrogen meets hydrogen, you get NH3. NH3 can fall apart and make nitrogen and hydrogen. You got a forward reaction or a reverse reaction. Solubility equilibria are also a thing. Salt can be in equilibrium with the sodium and the chlorine that are dissolved in the water. So you can have, solid, the liquid. If you've ever boiled off some salt water, you'll note that the solid just comes right back out as you reduce the amount of water, because the reverse rate becomes faster. It's quite interesting. And then there's like vapor equilibriums, the equilibrium between a liquid and its vapor. So water turning into water vapor is one such equilibrium, and it gets faster with higher temperature until you get to boiling point when it's all turning into a gas very quickly. So those are some examples of chemical equilibrium, of dynamic equilibriums. And in terms of concentration, N2O4 becomes 2NO2. Every one of these becomes two of these. There's a certain time here where you get that dynamic equilibrium. Right? Now they're going to do their forward and reverse processes. But the relative amounts are going to stay the same. And that's what we call the dynamic equilibrium. That's the equilibrium position. And it doesn't matter where you start, you're going to end up at equilibrium position. So notice that the final concentrations here are the same between the N2O4 and the NO2 when we start with equal numbers when we start with the number of atoms being correct. All right, this one starts with 0.75 moles per liter. This one starts with 1.5 moles per liter. This one needs to be twice as much because there's two of them. That's why there's the 1.5 there. But if you start with everything NO2 or everything N2O4, you end up with the same final concentrations, because when you start with all products, the reverse rate is very quick. When you start with all reactants, the forward rate is very quick, but eventually they're going to equalize, right? It's either like this or it's like this, but they're going to get to that same rate. Notice that it's not equal, it's at equilibrium. This is an important distinction to make. Next up, we're going to talk about LeChatelier's principle. This is just talking about how concentration, like rate, depends on concentration. Rate depends on concentration because the higher the concentration, the higher the probability of collisions. And we have this shorthand for moles per liter. Moles per liter. Specifically talking about concentration in moles per liter. So the square brackets are what we're talking about. That's what we see here. And then we're going to talk about LeChatelier's principle. So I'm going to pause and we'll talk about LeChatelier's principle. Let's talk about LeChatelier's principle. It's a pretty simple question that he had. It was what happens when we disturb the system. He would like mess with quantities of reactants and products. He'd heat stuff up. He'd cool stuff down. And he was working on that kind of stuff. So thought experiment. Let's say I have this equilibrium. NO2 plus NO to N2O plus O2. Don't worry about the K value. We'll get to that later. But here's the forward reaction is NO2 plus NO to N2O plus O2. Reverse reaction N2O plus O2 going back. And I've got it in equilibrium, right? The forward rate is equal to the reverse rate. What happens if I add some NO2, some of this stuff? What if I increase the amount of NO2? What will happen? Well, let's think it through based on what we've already learned about reaction rates, right? More NO2. I'm going to use that shortcut that we use, right? More concentration of O2 means what for the reaction rate? Which rate goes faster? Well, it's going to be the forward rate. We have more NO2s. There's more chance that the NO2 hits the NO, right? There's more chance of that effective collisions. More chance of effective collisions in the forward direction, right? More chance of effective collisions in the forward direction. This means the forward reaction, it means the forward reaction will move faster. Right, forward reaction goes faster, and the forward reaction is NO2 plus NO becoming N2O plus O2. So, so we're going to make more N2O and O2. More N2O and O2. And this is the really interesting part. The amount of NO will decrease. Right, the equilibrium amount of NO the equilibrium amount of nitrous oxide will decrease. Of this stuff, it'll go down. When I add this stuff, this will go down. And these will go up. So I only added the NO2, but I'm going to have a decrease in NO and an increase in both of these. And the reason for that is because the forward rate will go faster, because I have a higher chance of collision here. The reverse rate will catch up very quickly because as this increases, now the reverse rate is going to increase in speed and the forward rate is going to decrease in speed. So you'll get a new equilibrium. So it's like basically it was like this, then I did this, and now it's going to kind of do that, right? So I increased this, and now it's going to find a new equilibrium a little bit higher. But in order to do that, right, I increased this higher. This comes down a little bit, and coming down reduces the amount of nitrous oxide of NO in my reaction. So that's LeChatelier's principle. He stated it, you know, one easy way to state it is when a change is made to a system at equilibrium, the system adjusts to counteract the change. Right? Notice here I increased the NO2. The system acted to decrease the amount of NO2. It pushed the equilibrium. We sometimes say that it, you know, the equilibrium shifts that way. The equilibrium will shift that way. Right. So here's a real world example. Opening a Coke bottle. Here's an equilibrium in the Coke bottle. Gaseous CO2 and aqueous H2CO3. When you open the Coke bottle, the amount of CO2 decreases. All right, opening the bottle. The amount of CO2. It decreases the amount of CO2. Right, and because it decreases the amount of CO2, now this reaction slows down. So the reverse rate slows down. The reverse rate slows down. So then the amount of H2CO3 is going to decrease. Right, the forward rate will now dominate the reaction. Lots more CO2 is released. That's the kind of thinking that we need to be used to. You guys know that when you open a Coke bottle, a bunch of bubbles come out. Well, those bubbles are from the forward reaction producing CO2. It was already doing it, but there was a reverse reaction of the CO2 coming back and making the carbonic acid here. When we release the CO2, that forward reaction is still ongoing, and it releases a bunch of CO2 up into the atmosphere. Another interesting example is if you add acid to some magnesium hydroxide, the acid, the H+, will react with the OH-, right? The H+ will react with the OH-, decreasing the concentration of OH-, right? Decreasing the concentration of OH-. And that pushes the equilibrium forwards, right? The equilibrium, if we want to use LeChatelier's principle, equilibrium will counteract that decrease by using up mg OH, right? Our new equilibrium will use up MgOH2. Oh wow, that 2 should be on the other side. Let me just fix that. There we go. Yeah, so this is the concept, is if we're changing our concentrations, the equilibrium will fight back against that change in concentrations. And usually I do a bunch of demos for this in class, but I can't because it's virtual learning. It's actually very useful in industry. So for example, we're going back to the Haber-Bosch process. When they're making this stuff, they want to make the ammonia to use it to make fertilizer. They constantly remove the NH3. As they remove the NH3, the equilibrium wants to shift to make more NH3. And because they're constantly removing it, the reverse reaction never compensates. So you're just making more and more and more and more ammonium, more and more NH3. That's LeChatelier's principle. Changes in temperature. Here's an exothermic reaction. This has a very, it's very exothermic. It's very likely to go this way. If you heat it up, remember our Boltzmann coefficient. When we heat it up, the more of the particles get to their activation energy. But there's actually 2 activation energies here, right? There's 2 activation energies. There is the reverse reaction activation energy as well. So the forward rate is exothermic. The forward reaction is exothermic, so it has a low activation energy, right? Exothermic reactions have a low activation energy. So most of the particles already have that amount of energy. But when we make it hotter, the higher temperature, you get way more favoring of that reverse rate than you do of the forward rate. The forward rate also increases, but the reverse rate increases much more because you're affecting this end of the tail, this end of the distribution. So basically, LeChatelier's principle still applies. If you take an exothermic reaction and you heat it up, the reaction will, the side that the forward versus reverse, the side that speeds up is the one that's endothermic. Heating something up speeds up the endothermic reaction more than it speeds up the exothermic. Same thing with cooling something down. Cooling something down will speed up the exothermic reaction, will slow down the exothermic reaction less than it'll slow down the endothermic reaction. Yes. Slow down the endothermic less than it'll slow down the exothermic. And so that's what we see. Here's a real-world example. Here's N2O4 to NO2. The N2O4 is colorless, and the N2O2 is reddish brown. This is at room temperature. This is in ice, and this is in hot water. There's a hot plate there. And what you see here is this is an endothermic reaction. It's endothermic. And so when they increase the energy, the forward reaction becomes more likely, right? The forward reaction becomes more likely. So that's the hot water. They're increasing the energy, so the hot water, you get more brown. When they decrease the energy with the ice, the reverse reaction becomes more likely, and so their equilibrium pushes towards the colorless. You can think of it as when you increase the energy, the reaction will push to the side that decreases energy. So when the energy goes up, the reaction will act to decrease the energy. It'll fight back. So you're increasing the energy, it'll go to the side that has less energy. It'll go to the side that has less energy, right? It'll push that way. If you decrease the energy, it'll push to the side that makes energy. It'll release energy to compensate. That's one way to think about it. So the system fights back is basically the idea. Okay, the last piece here, gas phase, right? Gas phase is the other thing. LeChatelier's principle with gas phases is interesting because of pressures. You can actually affect the pressure by increasing or decreasing the pressure of the entire system, but only by squeezing. And what happens there is you just get more collisions, right? And when you squeeze it, you get more collisions, just like heating it up or cooling it down. You get more collisions, and when there's more collisions, the side that has more collisions becomes faster. And so when we squeeze this, when you go high pressure, this will push towards the lower pressure side. And that pressure, if you remember from grade 11 chemistry, that pressure is based purely on the number of molecules, not how big they are or anything like that, just the number. So here we have 4 gas phases. There's 4 gas phase molecules here, 4 gas molecules on this side versus just 2 gas molecules on this side, right? 4 gas molecules or 2 gas molecules. So if you increase the pressure, it'll push to the side with less pressure. If you decrease the pressure, it'll push to the side with more pressure. It fights you again. If you're trying to increase the pressure, it fights you by going to the lower pressure side. If you try to decrease the pressure, it fights you by going to the higher pressure side. But this is only if you increase the pressure on all of the gas at the same time. It has to be partial pressure. And this is how those SodaStream machines work. They increase the pressure of CO2 above the water, which forces the CO2 into the water. It's using this same reaction back here, this one. It's increasing the amount of CO2, so it forces it into the water to decrease the pressure. Now there's some things that don't affect the equilibrium. One thing is solid state reactants. If you have some kind of solid and you add more solid, you're not going to affect the equilibrium because you're not changing concentrations. You're not changing the concentration. Well, I can't spell concentration. Solids, they kind of have a constant. Reactants have a constant concentration, right? So that doesn't work. Yeah. So like, imagine you have a reaction happening in a Coke bottle, and you drop in, a piece of metal. It doesn't really do anything. I guess it has to be part of the reaction. Maybe the solubility equilibrium. If it's already going back and forth and you just add more solid, nothing's going to happen. Adding an inert gas is another one. So like if I have this reaction set up and I try to increase the pressure by adding helium, that one's kind of hard to explain, but you got to remember that it's collision theory. It's if these collide, specifically the nitrogen collides with the hydrogen, you're going to get the reaction. If there's helium in there, the nitrogen is going to collide with helium instead of colliding with hydrogen. So it doesn't actually change the partial pressures, and it's not going to change the rate of reaction. So you're basically adding something that's not taking part of the reaction, so you're not going to change anything. Then catalysts. Now this is really interesting. Catalysts do not affect the position of the equilibrium. Catalysts do not affect LeChatelier's principle. There's two ways to think about this. The first way is you're not actually affecting the reactants or the products, you're just affecting the method by which they turn from reactants to products. The second way to think about it is that you're lowering the activation energy for both sides. For both sides. If we go back to here, it's like imagining if we were back here where they had equal cups, and we gave both of them big cups. That would be the equivalent of putting a catalyst in there. They both have big cups now. They're a lower activation energy both ways. It's still going to be equal both ways. All right, so a catalyst does not affect the rate of the reaction. Yeah, and that's it. We'll do some practice problems with this in class. I realize it's a little bit confusing when I talk about it, but when we do practice problems, it'll be a lot easier to explain. Please watch that video, the demo with the water down below. It's really useful. And yeah, I'll see you guys in class. Thanks a lot.